You built a working LangChain chain. Now you're connecting 3 steps, and suddenly, context disappears. This video shows exactly why that happens and how LCL solves it. Here's the trap. You chain your first model call into your second. The second call needs your original question, but it only receives the first call's output. Your original question? Gone. This is context loss, the silent killer of multi-step AI pipelines. Most tutorials show a 2-step chain that works. They never show you step 3, when you need data from step 1, but you're already past it. Today you'll see exactly why this breaks, and you'll learn the 3 LCEL primitives that fix it permanently. Let's define what we're building. A sequential chain is multiple LLM calls connected in order. Output from step 1 feeds into step 2. Step 2 feeds step 3. Think of it like a recipe. You don't drop raw eggs into the final batter. You beat them first, let them set, then fold them in carefully. Each step transforms the ingredient before passing it forward. The challenge? LangChain's pipe operator only forwards the immediate output, nothing else. According to the official LangChain LCEL documentation, every runnable receives 1 input value and emits 1 output value, 1 in, 1 out. So if your step 3 prompt needs step 1's data, the pipe won't carry it. You must route that data explicitly at every junction. Before writing any chain code, design your prompts. This is the step most developers skip entirely. In a sequential pipeline, every prompt template must explicitly declare every input variable it needs, not just the previous step's output, every variable from every upstream step it depends on. Let's build a blog writing pipeline. Step 1 extracts the main topic. 1 variable needed, question. Step 2 writes the blog post. 2 variables needed, topic and question. The post must stay grounded in what the user actually asked, not just drift on the extracted topic. Step 3 summarizes for a general audience. Also 2 variables, blog_post and question. Write all 3 templates up front. Declare every variable before you wire a single pipe. This design-first approach prevents mysterious variable key errors downstream, the kind that have no obvious error message. Now let's see the naive approach fail. Chain 1 is step 1 prompt pipe model, pipe str output parser. That outputs a plain string, the extracted topic. You pipe chain 1 directly into step 2 prompt. Run it, it crashes. Step 2, expected 2 variables, topic and question. But the pipe only sent it a plain string. Str output parser converted everything to text. There's no question key, there's no topic key, just unstructured text. LCEL cannot magically split 1 string into 2 prompt variables. This is not a bug, it's correct behavior. The pipe forwards exactly what it receives, 1 string in, 1 string out. Your step 2 prompt needed a dictionary with 2 keys. It got a string. That mismatch is the entire problem. Here's the fix. Instead of piping chain 1 directly into step 2, insert a dict step between them. In LCEL, a plain Python dict sitting in your pipeline is automatically converted into a RunnableParallel. This is the non-obvious insight most LangChain tutorials skip entirely. You write, open brace, topic : chain 1, comma, question : RunnablePassthrough, open and close parens, close brace. LCL sees that dict. It runs chain 1 and RunnablePassthrough simultaneously on the same input. Chain 1 transforms the input into a topic string. RunnablePassthrough returns the original input unchanged. The dict step emits a dictionary, topic string plus original question string. Now step 2 has both variables it needs. Think of RunnablePassthrough as a glass pipe. Water enters and exits exactly as it came in. Nothing leaks, nothing transforms. It just carries the original value forward, invisibly, to any downstream step that needs it. Let's run the complete 2-step chain and verify it works. Import chat prompt template, chat OpenAI, str output parser, and RunnablePassthrough. Build step 1 and step 2 prompts. Chain 1, step 1 prompt pipe model pipe star output parser. Full chain, dict step with topic : chain 1 and question : RunnablePassthrough, piped into step 2 prompt, piped into model, piped into str output parser. Invoke with a plain question string. Watch the output. The blog post addresses the exact mechanism the user asked about. Grounded, contextual, not just floating on a topic in isolation. 7 lines of LCEL. Compare that to the deprecated legacy sequential chain approach, which was removed in LangChain 0.30 according to the official migration guide, where class inheritance and hidden magic made the data flow opaque and untestable. But here's where it breaks again. You add step 3. Step 3 needs the original question, and it needs the blog post from step 2. After step 2 runs, you're back to a plain string. The question key is gone. How do you preserve a dict key through a step that outputs a plain string? This is where itemgetter comes in, and it changes how you think about multi-step data routing entirely. After your first dict step runs, the flowing value is a dictionary. Topic and question are both present. Step 2's prompt plus model plus parser consume that dict and return a plain string. The question key disappears. To preserve it, add another dict step. This time use itemgetter from Python's operator module. Write blog_post : the step 2 chain, comma, question, itemgetter of quote, question, end quote. Itemgetter extracts one specific key from the incoming dict and passes only that value forward. Think of it like a mailroom worker. They open the incoming shipment, pull out only the invoice, and send it separately. The original package travels elsewhere in the system. Itemgetter is your surgical extractor. RunnablePassthrough forwards everything unchanged. Itemgetter forwards exactly one key. Different tools, different precision. Now the climax demo, a real-world code review pipeline, 3 steps. Step 1, analyzes code and lists bugs. 1 variable, code. Step 2 suggests fixes. 2 variables, code and issues. Step 3 writes the final report. 2 variables, code and fixes. Build 3 prompt templates. Chain 1 is the analysis prompt pipe through model and parser. Full pipeline. First dict step, issues : analyze chain, code : RunnablePassthrough. Second dict step, fixes : fix chain, code : itemgetter of code. Then report prompt pipe model pipe parser. Invoke with a raw code string. Step 1 gets the code. Step 2 gets the code and the issues. Step 3 gets the code and the fixes. No context loss, no missing variables. The original code string travels through every step, exactly where it's needed. Here's the mental model that ties everything together. An LCEL chain is a data flow graph. Every node receives one value and emits one value. The pipe operator moves data forward, never backward. If a downstream step needs upstream data, you must route it explicitly at every junction between them. Dict steps are your junction boxes. RunnablePassthrough is your straight-through connector. Itemgetter is your precision extractor. Once you see your chain as a data flow graph, design becomes a routing problem, not a coding problem. Map what each step needs. Identify which upstream data must travel to it. Build the routing to deliver it. That's the AI engineer's mindset, and it scales to any number of steps. If sequential chains finally clicked, subscribe. Next video, RAG with LCL. You'll see RunnablePassthrough and itemgetter again, this time routing retrieved document chunks directly into your prompts. Same primitives, completely new use case. Code for this video is linked in the description. Now go build a chain that actually remembers its context. I'll see you in the next one.